Hey guys, what's up? So this is going to be kind of a review to help you out on the Angle Projectiles Formative 1 from our digital day assignment. So just going to kind of work through this and kind of help lead you through as we go. All right, so this is the first problem. I don't know how well you can read this with the projector and the camera going, but what we got is a member of the JCH Soccer Football Club kicks at an angle of 38 degrees. So I'm going to find the, let's see, so we got 38 degrees. Off the ground with an initial speed of 15 meters per second. Okay, we want to know how long is the ball in the air, right? We want to know how far down the field does the ball land. We want to know what is the max height that the ball reached. All right, so the first thing we want to know is how long is the ball in the air? So if we think about our parabola motion, okay, so there's our trajectory right there. Now, we know, if we think about this vertically, whatever our initial velocity is here, at this point, right, at the top, it's going to briefly stop before it starts to fall again at the top of that trajectory, top of that parabola. So up here, we know we got 0 meters per second. So we have initial velocity, we have a final velocity, we have the acceleration because we know we're on Earth. Unless told otherwise, we will assume we're on Earth. So we know that our acceleration is 9.8 meters per second squared, right? And we're looking for time. So this will lead us to using this formula here. Now, we know our final velocity is 0. So final velocity, 0 meters per second equals. For our initial velocity, we cannot just plug in 15 meters per second because that is the angled launch velocity. We got to break this thing down into vertical and horizontal, right? So if you look at your formula sheet, you'll know that the vertical, to find that out, right? You know the whole SOHCAHTOA thing we went over, right? So we would know that we would do 15 sine 38. Okay, so for our vertical, if we're trying to use our vertical velocity, our initial velocity, we would use 15 sine 8. If we're looking at our horizontal, we would use 15 cosine 38, right, to find these things. So this would give us our either, this one would be our initial velocity for y, which is vertical. This one would be our initial velocity x, which is horizontal, right? X, y. So in this case, we're talking about vertical motion. So we can sub this in, right? So it'll be 15 sine 38, okay, plus our acceleration is 9.8 meters per second times t. Right, now to solve this, okay, using our mathematical situation here, we go ahead and figure out what this is, right? So let's just say, here's my calculator. Work through this one a little more detailed, I guess, with you than the other one. So if I work that out, this is, right, okay, 9.23 meters per second. So we got meters per second addition. Okay, so we're going to go ahead and subtract 9.23 meters per second. From this side, whatever we do to one side, we must do to the other side, 9.23 meters per second. So if I rewrite what I got at this moment, okay, I got negative 9.23 meters per second equals 9.8 meters per second times t. Okay. From this point, you're just solving for x, right? You divide both sides by 9.8. Oh, this is negative because we are slowing down to 0, right? So that's my bad. Got in a rush. Okay. Okay, so if we look at this before we solve, right? Meter, meter, second, second. So our answer, right, after you do this, your answer is going to be in seconds. And that is a unit for time, so we know we are correct. So when we work this out, we get .941. Now, that is not the total time. That is not our answer for A. That is how long it took to go from launch to where it stopped at the top of our parabola, the top of our trajectory or whatnot, and started to go down. So half of our flight time is 0.941 seconds. Right? We know the acceleration of it slowing down is going to be equal to the acceleration of it speeding up, because acceleration of gravity on Earth doesn't matter if you're going up or down, right? So the other second half of our trajectory also took the same amount of time. So our total flight time, 1.88 seconds. So the answer to A, how long is the ball in the air, is 1.88 seconds. Now, moving on to B. B wants to know how far down the field does the ball land. So this, okay, how far down did it go, right? This is change in X. How far did it change? What is the range? A lot of different ways you can ask this. But so we're looking at X, so we know we're thinking about, 15 cosine 38 gives us our horizontal component. So, find this out. You go, make sure I don't write this right. So you use the formula D equals VIT plus 1/2 AT squared. Now, because we are talking about horizontal motion, there is no horizontal acceleration. So if the horizontal acceleration is 0, these things times 0 would cancel out. So then we're just left with this part of the equation. So our distance, or our change in X, is equal to our initial velocity. Okay. To find that for our horizontal component, we're going to do 15 cosine 38 times our time. Our time for the entire thing is 1.88 seconds. Okay. This, once you work this out, right, remember, meters per second, right? If you multiply this together, right, because this is meters over seconds, our seconds cancel, our answer is in meters, and that's what distance is, and that's a unit that we can use for that, so we know we're in the right shape. So if you work that out, you'll get the answer to B. Next up is C. What is the max height the ball reached? So what is from here, right? What is the max height? Okay, so we're going to use this formula again. D equals VIT plus 1. Okay. Now this time we do have an acceleration. Okay, and we know we're talking vertical again. We're talking vertical. It's 15 cosine. 15 sine 38. Sorry, I did that one for you. What was that? 15. So when I'm looking for my change, this is y, right? We're looking at the distance y. We're going to go initial velocity, which is 15 sine 38, which is 9.23. Our time, we're not going to use the time of the whole flight. Okay, by this time we're already back down to the horizontal, to the ground level. Our max height is going to be right there in the middle. So we're going to go 0.941 seconds plus 1/2 acceleration, 9.8 meters per second squared, 0.941 seconds squared. Right, so now it's just, please excuse my dear Aunt Sally, right? You do your exponents first, multiplication next, and then you can come together and add it together. All right. So meters per second squared, you multiply these two together, seconds squared, right? Second squared, meters, so forth. Cancel out your units, you should be ending up with meters at the end there. All right, so that completes question 1. All right. All right, so here we have question 2. Right, I don't know how good you can read that. Coach High tees off on 186-yard par 3, so 170.08 meters. Slings the club full go, roughly 51 meters per second. Grabs a 7-iron out of the bag, which has a loft of 30.5 degrees. So we're sitting here, we're thinking, 170 is the goal. We got 51 meters per second, 30.5 degrees. Okay, we want to know how far will Coach High's golf shot travel, and did he select the right club? All right, so for this one, pretty much can't do anything without time. All right, so for 1, 2, and 3, we're going to solve for time the same way. We know we got parabolic motion. We know it's going to go up and back down. The acceleration going up is equal to the acceleration going down. So at our midpoint, we're at 0 meters per second. So this is our final velocity. So for this one and the next one, we're going to find time like this. So we're just going to set it up. VF equals VI plus AT. Okay, so we know our final velocity is going to be 0. We know we're talking about vertical motion. Okay, so we're going to take our initial right there. So this will be 51 meters per second sine 30.5. Okay, that'll give us our vertical component. Minus, we're slowing down, 9.8 meters per second times t. Okay, and you're just going to work that out just like we did the last one. You'll end in seconds. Then you'll remember, okay, whatever this gives us, x seconds, solving that, I'm just saying x seconds, is the time from here to there, right? So you need to double that for your entire time, right? Now, once you have your time, okay, then you can go on to figure out, how far will the shot travel? And remember, we're not taking into account spin of the golf ball, wind that day, air resistance, things like that. This is just like, hitting it into a vacuum. So, but what's the basics, right? Got to get the basics down before you can move on. So to figure out how far, right, we're not concerned with how far up in the air. We're talking about the distance, right? So that's the range. So distance or displacement equals VIT plus 1/2 AT squared. Remember, horizontal range, 0 acceleration, so we're going, right? Displacement equals your initial velocity. Now we're talking about change in x, right? We're talking about horizontal. So for VI, we need our horizontal, which is 51 meters per second cosine 30.5 times t. So whatever you got for t, right, goes in here. As far as did he choose the right club or not, that's up to you to decide. One answer I got wasn't what I was looking for, but for the non-golfer, it makes perfect sense. So kind of leaving that one up to your judgment call. Number 3. All right, so this one for number 3, we got the punter in an American football game kicks the ball from the goal line, which is the 0-yard line. The punter launches it at 60 degrees from the horizontal at a velocity of 25 meters per second. It gives us this conversion factor here, right? So that's important to remember. We got 1.0937 yard equals 1 meter. What is the hang time of the punt? How far downfield does the ball land? This is just asking for the time of the entire flight, right? That's how long it was in the air. And this one is asking how far down the field does it go. Just like before, to find our hang time to find our amount of time in the air. Remember, parabolic motion, 0 meters per second. So our final velocity, initial velocity, this is vertical, right? This is our vertical component, so we're dealing with, I don't remember what the dang, 25 meters per second at 60 degrees. So 25 meters per second at 60 degrees. Okay, that's our vertical component. Slowing down, solve for t. All right, just like we did on the first two, you're going to solve for t. It's going to give you X amount of seconds. Then the next part of it was for B, how far downfield does the ball land, excluding roll and all that. So that's just looking for your change in X. That's just D equals, right, VIT. This cancels because there's no horizontal motion. D equals horizontal, right? Horizontal is going to be 25 cosine 60. And then whatever your time was, remember to double it. Remember to double that time because that's just your half flight, right? So double that time for your whole flight and then put it in right there, and that'll give you your range. All right, so this one is the last one, number 4. So ever wonder how far you could throw a ball on Mars? The acceleration of gravity on Mars is 3.721 meters per second. So now we have a new acceleration that we might deal with. So I'm going to make note of that. Okay. Okay. I'm thinking that the average person could throw like 45 to 50 mile an hour. So let's assume the average velocity of humans throwing a ball is 47 miles per hour. Okay, we got a conversion factor of 1 miles per hour equals 0.44704 meters per second. And then it's going to ask us, our launch angle is going to be 45 degrees above the horizon. So basically it's just kind of comparing Earth and Mars, Earth and Mars, Earth and Mars, the impact of a different acceleration. So the first two, A, how far can the average person throw the ball on Earth? B, how far could the average person throw a ball on Mars? Okay, launching them at the same angle, the same initial velocity, which is 47 mile per hour, 45 degrees. Right. So first thing, let's get rid of this. Whoops. Yeah, I don't know if you can read that. That looks pretty bad. So let's get rid of the mile per hour and get it into meters per second. So if we have 47 miles per hour, right? For every miles per hour is 0.44704. Convert that real quick. That is 21. Okay, so there's our kind of initial velocity of our projectile. Now we want to know how far can the average person throw the ball on Earth versus Mars. So first thing, we got to figure out the time, right? So we'll say green is Earth, right? So for both of them, right, we're going to use VF equals VI plus AT. Right? And where both of them have the same projectile, we'll use our same thing. So for Earth, can we see right here? Yes. For Earth, we're going to go final velocity 0 meters per second, because that's going to be at the top of the parabola, equals, okay, now we can't use this because this is not in our vertical component form, so we're going to solve for this by doing 21.01 sine 45, right, plus or minus 9.8 meters per second, because it's slowing down, that's why it's negative, and then time. Mars is going to be same thing, 0 meters per second equals, so 21.01 cosine. Sorry, I jumped ahead. I had to pause it. Somebody had asked me a question. But, so these are the same. But with Mars, we don't put 9.8 right there because the acceleration is different. So we're going to go 3.721. All right, so you're going to work these out. Remember, this is going to give you the time from here to here on Earth. This is going to give you the time from here to here on Mars. If you want your whole time, you got to double it. Got to double it. All right, so now we have our time of our flight from Mars, going to be represented by a purple XT. We have our time of flight on Earth, which is going to be represented by a green XT. So we're still working on A and B. How far can the average person throw it on Earth versus Mars? So we'll go ahead and set that up for Earth. Remember, we're looking for horizontal change in X. So displacement equals, right? So horizontal, right, is going to be 21 cosine 45 xt. Okay. Remember, our equation is d equals vit plus 1/2 at squared. We scratched the second half because there is no horizontal acceleration. So this is for the Earth. This is for Mars. So this exact same thing, except with our times being different due to what we worked out first. Right? So you plug this in here, that one in there. This will give you your distances thrown on Earth versus your distance thrown on Mars. C and D is how long will the ball be in air on Earth? D, how long will the ball be in the air on Mars? So you already worked that out. You just got to go back and find that data where you did it before. E and F is height. So range or max heights. How high above the Martian surface or high above the Earth's surface? So for Earth, okay, how high? So this is vertical, right? Distance equals 21.01 sine 45. Earth time goes here plus 1/2 Earth's gravity, right? 9.8 Earth's time squared. Solve it. Please excuse my dear Aunt Sally. Follow your rules. Gives you your height on Earth, your change in Y. Mars starts out the same, 21.01 sine 45. The time for Mars, the gravity for Mars, the time for Mars again. Solve it. Please excuse my dear Aunt Sally. Last question is, would you say there's a significant increase in one's ability to throw the object on Mars versus Earth? Again, that's just kind of up to what your data says. All right, good luck. Let me know if you need any clarification on anything.